Hello and welcome. Today I want to introduce you to two important reactions that are targeted specifically at topic 10.2 for IB chemistry. These reactions are nucleophilic substitution and electrophilic substitution. Now both of these reactions will be developed further in HL chemistry topic 20, but for the purpose of SL chemistry topic 10.2, this is exactly what you need to cover. An example, first of all, of nucleophilic substitution, dealing with this halogennoalkane here. As you notice, CH3, the alkyl group, has got one chlorine atom attached to it. It exists as a gas, and this is reacting with sodium hydroxide in aqueous solution. And here you see that chlorine is replaced by OH, hydroxide, a substitution therefore. And the chlorine then combines with the sodium to form sodium chloride. But what is of significance is the presence of the OH with its lone pair and how it approaches this carbon here, which has a small positive charge because of its attachment to the very highly electronegative chlorine. This bond here is a polar bond, and therefore this species, OH with its lone pair and its negative charge, is searching for some area of positivity to interact with. That is where the term nucleophilic comes from. In search of a file, in search of positive center, nucleophilic, and it removes the chlorine. Here you see this double-headed arrow symbolizing that a pair of electrons goes over this way, and this pair of electrons comes in this way, and chlorine is pushed out, and hydroxide comes in its place, and you have a nucleophilic substitution. Hydroxide is described as a nucleophile, and it can also be described as a Lewis base. A Lewis base being a species that has a lone pair which it can donate to another species. So that's one of the two important reactions I want to highlight to you in 10.2. The other one is electrophilic substitution. And the example for SL students is this one here, where benzene C6H6 reacts with bromine. Both of these in a non-aqueous environment. It means that water is not the solvent. In the presence of this FeBr3 catalyst, one of the hydrogens on C6H6 is replaced by a bromine. So what you have here is C6H5Br, a substitution again, and that hydrogen that's lost is picked up by a bromine. But how does this electrophilic substitution happen? Well, Br2 has to first be polarized. And this is why you need the iron bromide catalyst. In the presence of this substance, bromine interacts with it, giving over a lone pair of electrons to it, and this FeBr3 accepting that lone pair. And in so doing, it behaves as a Lewis acid, a lone pair acceptor. It's also behaving as an electrophile in that sense, because a Lewis acid is an electrophile, a Lewis base is a nucleophile. And once that happens over here, then this part of the Br becomes positively charged, and therefore it can associate with the pi electrons in this benzene ring. This positive entity searching out a negative area with all of these electrons. When a positive entity or positive charge like this seeks out a negative area, we have something that is searching for something negative, electronegative. So it's in search of a negative center because it's positively charged, attracted to this negative center with the pi electrons on the benzene ring, pushes out a hydrogen and takes its place. And that's why this reaction is called electrophilic substitution. So the reaction between benzene and bromine in the presence of FeBr3 catalyst, an example of electrophilic substitution, and the reaction between a halogenoalkane and a hydroxide ion or sodium hydroxide, an example of nucleophilic substitution.